Hello, my name is Sultan Al-Niyadi and I'm an astronaut living and working on board the International Space Station. Any idea how it's possible for the space station to continuously orbit Earth 250 miles above the surface? And why at 17,500 miles per hour? What would happen if the station sped up or slowed down? We are going to explore those questions and more by investigating the connection between the angular momentum and the orbits in our microgravity environment. But first, you need to know a couple of other terms.
Let's get started. Before we dive into centripetal force, it's important to look at Newton's first law of motion, which states that an object will continue moving with a constant velocity along a straight path unless acted upon by a net external force. This means that the space station will move along a straight path if it weren't for one key external force acting on it, Earth's gravitational pull. Another name for this external force is centripetal force. A centripetal force is any net force that keeps an object moving along a circular path. Gravity, in this case, is a centripetal force because it is the force that is keeping our space station moving in its circular path around Earth.
Okay, now you know that gravity constantly pulls the moving object with linear momentum inward just enough to cause it to travel in a curved path, making its momentum angular. The International Space Station maintains this balance between gravity and linear momentum by traveling at the required 17,500 miles per hour to maintain an altitude of 250 miles. This is considered low Earth orbit. It is high enough to encounter very little interference from the atmosphere, but low enough to be relatively easy to travel to. Let me show you some examples of angular momentum being conserved in the microgravity environment aboard the station. I will apply a force to set this yo-yo in motion. The force of tension is transferred through the string, which is a centripetal force keeping this yo-yo revolving around my hand. But what happens when I let go of the string? Once the tension from the string is removed, the object continues to follow Newton's first law of motion. It keeps moving at a constant velocity along a straight path relative to the space station. Now, what happens to the motion of the yo-yo if we increase the centripetal force by increasing the tension in the string? As I'm holding the string between two fingers on one hand to keep the axis of the rotation stable, I'm going to pull the string with my other hand, increasing the tension and centripetal force and decreasing the radius of the yo-yo's orbit. As the radius of the yo-yo's orbit decreases, its velocity increased. Angular momentum is a product of an object's velocity, mass, and the radius of its orbit from an object's center. If you only have centripetal force, angular momentum must also be conserved. So if the radius of its orbit decreases, its velocity must increase in order to maintain its angular momentum. Let's try this again, but this time I'll decrease the tension on the string, lowering the centripetal force and increasing the radius of the yo-yo's orbit. If you thought the velocity of the yo-yo would decrease, you were right, since angular momentum must be conserved. If the radius of an orbit is increased, the velocity of the yo-yo must decrease. As you can see, there is an inverse relationship between the radius of the orbit and the yo-yo's velocity. I was able to change the velocity of the yo-yo by increasing and decreasing the centripetal force in the system. We can't do this with the orbit of the station or other satellites because we can't change the pull of gravity exerted by Earth. Instead, to keep the station in a stable circular orbit, we use thrusters that can help maintain the constant speed of 17,500 miles per hour. To learn more about these topics, check out the corresponding classroom connection to conduct your own experiment and discover other ways angular momentum plays a part in your daily life. Thank you for exploring some physics with me today, and see you soon.